Okay. It's a great pleasure to introduce our speakers tonight, Dr. Antonio Paris and Dr. Evan Davies. Dr. Paris is both a geophysicist and an astrophysicist, an unusual but quite logical combination these days. He has applied to Mars and to other astronomical objects some of the insights he's gained from his research on geophysical phenomena. In his research in geophysics, he's developed innovative methods of using space-based remote sensing to characterize river flows in regions that are difficult to access, such as the Amazon. And he's also developed and then tested sophisticated models of terrestrial rivers, which would be a very complicated thing. And devising good tests is very non-trivial. In astrophysics, Dr. Paris is chief scientist at the Center for Planetary Science. He's been a professor of astrophysics at St. Petersburg College in Florida. He's a graduate of the NASA Mars Education Program at the Mars Space Flight Center at Arizona State University. One result of his research in astrophysics has been a useful proposed explanation of a puzzling radioastronomical signal that is widely known as the WOW signal. He showed how clouds of atomic hydrogen from two particular comets could have caused that signal. He's also combined his geophysical and astrophysical interests by analyzing whether a recently identified crater in Egypt was produced by an impactor from outside the Earth. He's done extensive research on the implications of prolonged spaceflight, including the effects of radiation, how the cardiovascular system will stand up, and long-term nutritional concerns in microgravity. In particular, he's analyzed the physiological and psychological aspects of sending humans to Mars. Tonight he'll tell us about an ingenious proposal to use a type of geological feature that occurs on Earth and on Mars to protect future visitors to Mars.
Thank you. Thank you for inviting me. A couple days ago, Dr. Davies, who's got more of a background in medicine and a little bit anthropology, he actually helped me with this research as well as other studies. And I thought, hey, would it be a great idea if you just came with me and talk a little bit about the radiation aspect, like long-term radiation aspects on a planet that has very little atmosphere and the implications of staying too long on the surface. So we're probably going to go back and forth a couple of times so he can talk about his background, his research on radiation on Mars and maybe some deep space radiation as well. So that was a big introduction. If I can bring it all down into one quick couple of sentences, I'm a planetary scientist. I got my PhD at University of London in astrophysics, but it's such a broad subject. I wanted to do something that was more related to Earth science, something close, something that I can actually apply to right here on Earth. So I started looking around what I was interested in, and about 5 years ago, NASA invited me to ASU. It was a new program called Your Curiosity. The Curiosity rover just landed, and they needed scientists to look at the data that the rover was bringing back. So hence the birth of planetary science. In the last 10 years, I was able to be part of that. And I said, hey, wait a minute. So I'm an astronomer. I'm in the desert digging through dirt, right? So I was like, I'm kind of like a geologist / planet astronomer. So I kind of fell in love with that, being in the field as opposed to being in an observatory looking at a quasar or something. Which that does, well, that was fun. That appealed to me. But I thought being in the dirt, looking through some analogs in the throughout the states, I thought that was pretty neat for me. So I kind of shifted away from astronomy, away from astrophysics and black holes, and more to something where I can actually put a backpack on and do some digging. So for the last 5 years, I've been looking at Mars in particular, as well as the moon. And now recently, I'm kind of moving beyond Mars, and Evan and I are looking at what's the next step? What's beyond Mars? What are the moons of Jupiter that can provide us for survivability, as well as Saturn and Ceres and etc. But about a year ago, I was asked to look at how can we survive on Mars on a budget, right? Instead of spending trillions and billions of dollars on building habitats in orbit or launching them to Mars and then putting them together, what natural features on Mars can we use to leverage and perhaps also protect us from the radiation exposure? So I was looking at some lava tubes here on Earth, as well as the few that we found on the moon. And the studies have shown, at least here on Earth, from an analog perspective, that they could protect us from radiation. There's different ways we can leverage the lava tubes. Do we plug them in and pressurize them and use them, or do we bring like Bigelow Aerospace? They want to bring in inflatables, plug them into the lava tubes, and we can live that way. Or do we just use lava tubes initially and then build outwardly as we move along? So that is the focus of the next 45 minutes and an hour. A few of you have emailed me asking for a copy of my book. It's a pretty neat book. You put on 3D glasses and you learn about the geology of Mars. I only brought a handful because I had to carry on. But if you're interested, they're only $15. They're like 30 or 40 on Barnes & Noble. But if you want, I did bring a handful. So what are we going to talk about today? We're going to briefly talk about Mars facts, because everybody here probably knows what the planet Mars is. We're going to talk about Journey to Mars. There's a space race right now. Everybody wants to get to Mars, whether it's the private sector, the public sector. Is it the U.S. or is it an international effort? And then we'll get into the bulk, which is radiation on Mars. What are the risks? How can we leverage the volcanic features? How did I do my research, right? What data did I use? How did I find and discover potential lava tubes? And then what I like to do is we do the analog experiments. I found some lava tubes throughout the United States. My students and I went out there. We did some radiation experiments. And then we did some deductive reasoning experiments. And we'll talk about those conclusions. So we all love Mars. It's a terrestrial planet, just like Earth. Terrestrial is Latin for tierra. That means something that's rocky and land. It's often referred as to the red planet. I don't like that term, even though I even put it on my book, Red Planet, because it's so synonymous now with science fiction, so everybody uses the red planet. But theoretically and technically, it's a butterscotch planet, right? So I always tell my students, the butterscotch planet, and they're like, huh? But it's oxidized. The planet has been oxidized after years of erosion, and it's no different than a rusted bicycle or something. It's more of a butterscotch orange color. Terrestrial-wise, same as Earth, 4.5 billion years old. Temperatures, not too bad, minus 195 in the winter, but it gets about 70 to 80 degrees along the equatorial areas during the summers. From a long-term perspective, humans can survive there. It would have to be an artificial environment, however. One of the biggest questions that people ask me, can we terraform the planet and make it beautiful again? Really, no. You see that a lot in science fiction. And if we could do it, right, it's got no magnetic field, so it'd have to be an artificial magnetic field. And I think if it could be done, the cost was like $200 trillion, right? Who can afford that, right? Nobody at this point. But it's a nice planet. There's a little space race going on. There's a comparison for size. It's slightly smaller than Earth. It did have water once, we think, based on all the recent studies that we've been learning from the Mars Reconnaissance Orbiter, HiRISE, the rovers that we spent out there. We're starting, 20, 30 years ago, the big question was there water on Mars? Maybe. Today's like, was there water on Mars? Yeah, it kind of looks like it, just based on the data that we have received. So, in the late 90s, early 2000s, there was kind of a small space race going on with Sojourner and the small rovers. The administration came in, kind of cut all the Orion programs and all that stuff. And then not too long ago, about 7-8 years ago, the space race has begun again. Whether it's to the moon first and then a Mars trajectory. I think there's like 17 nations now building their space programs up. whether it's private, whether it's public, whether it's a combination of both. But everybody wants to go to Mars for many reasons, political reasons, financial reasons, whether it's for profit. So we'll see. The biggest question is who's going to get there first? Everybody thinks it's NASA. Maybe it could be NASA. I don't know. It could be China. It could be SpaceX. Personally, I think I was talking about this with my friends earlier. It would be nice in a real world if Boeing, Lockheed, SpaceX, NASA, ESA, Japan, India, all got together, build the spacecraft, and just let's do it together. But I don't see that happening. So what is the likely scenario? This is straight out of NASA's 2020 vision or 2030 vision. 2 to 8 is a nice crew. 4 to 5 year mission. It'll be a return mission. You probably see some private proposals for going on a one-way mission. That's a possibility. Mars One was the recent company that went bankrupt. They had something like 100 candidates to go to Mars. However, they quickly found out that it was a very expensive endeavor and they had to file for bankruptcy. Current estimates, about $1 trillion. $1 trillion in taxpayer money or private money to get to Mars for a 4 or 5 year mission. And as of today, Elon Musk says he can do it by 2024. NASA thinks it's more like 2039 to 2040, because that's the way the government works. But given any scenario, private, public, joint effort, getting to Mars is rather a difficult task, both from a technical perspective, engineering perspective, and also from a human perspective. So what are the biggest hazards other than the meteorite or the spacecraft malfunction? Probably the biggest ones now from a physical, human, medical perspective is going to be radiation. And we've been learning a lot about radiation, especially after the Curiosity flight trip. So the two biggest hazards of going to Mars or the Moon or any planet that has no atmosphere, for that matter, would be cosmic radiation. Cosmic radiation, including gamma ray burst, emissions from black holes, etc. Those will actually be dangerous to the human body, but more importantly as well, the spacecraft, there's no shielding. Where are the primary sources of gamma rays? They're going to be mostly from outside the solar system, whether there's active galactic nuclei, supernovas, or a gamma ray burst. In our neighborhood, it would be solar proton events, and those are either coronal mass ejections or these solar flares. Most of you know, any of these can just actually hamper spacecraft as well as any humans if they're in the vicinity of any of these two events. The solar flares do travel at the speed of light, so they get to Mars a little quicker, as opposed to a coronal mass ejection could probably take a couple of months. It was not until recently, for example in 2011, 2013, and the last one in 2017, that Curiosity rover started to detect these high energy proton events, and we'll talk about that later. Here on Earth, we're kind of lucky. We have something called the magnetic field. And the magnetic field is the kind of like the shield that protects us from all these nasty stuff that comes around. Some do, however, sneak by. If you have a radiation detector or a gamma ray detector, eventually sometimes you hear these little clicks. Some of these particle events do come through the atmosphere, not many, but you can detect those here on Earth. But for the most part, about 98% of that stuff is ejected outwardly, and that protects us from all these harmful events. However, on the lunar surface, most of the asteroids, and of course Mars, we don't have that luxury. Mars, for several reasons of unknown, whether it was an impact crater or the planet geologically died off quicker, it lost its magnetic field. And because of that, the solar wind, this is supposed to have a little animation. I guess it's not working. So the solar wind is not being ejected outwardly, and it's basically bombarding the surface of the planet constantly, and I'll tell you those numbers here in a minute. We don't know why the planet lost its magnetic field. One theory is it got hit by an impactor hundreds of millions of years ago. That could have been the cause. Other thinks that the planet cooled off a lot quicker, and people ask, well, what do you mean by that? The analogy I like to use is if planets are like potatoes, and you take a big potato, let's say that's Earth, and you take a tiny potato, and let's say that's Mars, you put them in the oven for about an hour, you take them out, they're both equally warm, right? Which planet will cool off cooler? Which potato? The tinier one, right? Planets are doing the same thing right now. Bigger planets are still relatively warm after the formation of the solar system. Smaller planets like Mercury, Ceres, etc., the dwarf planets, are cooling off a lot faster. There's a chain reaction to that. As the planets begin to cool off quicker, their cores die off, there's no longer a dynamo effect, and we lose the magnetic field. Once we lose the magnetic field, there's no protection, and most of the atmosphere is stripped away into deep space by the solar winds. So what is the recent studies that we've learned about Mars? There's two main missions from NASA, and the first one's called the MAVEN mission. And this one's still ongoing. About every year they do their measurements. And what have we learned? The solar wind is really nasty if you don't have any solar protection. So the MAVEN spacecraft, we did this measurements. If we're up here, up in the northern plumes, we get about 20,000 electron volts per hour. That's pretty bad. We don't want any spacecraft in orbit in that area because most of the equipment will be fried. So where do we land on Mars? Where's a good place to land on Mars? Probably in the mid-latitudes. You only get about 300 to 10 electron volts. That's pretty decent. Still bad, right? But anywhere between the equatorial areas to the possibly the solar, you want to be there to place spacecrafts or humans. And then the second mission was called the MADI mission. And this one, so this is what is the radiation environment from orbit? What is it we can detect on the surface from orbit? And then the second one was, what can we detect on the surface in particular? And what we learned is that areas that are highlighted in red have high levels of radiation, and those that are in blue and green have lower areas of radiation. So let's look at these numbers real quickly. The space station gets about 200 microsieverts per day. Not too bad. Still more than what we get here on Earth, but that's not too bad. Higher areas on the surface of Mars, we get about 600 a day. Now we're getting into an area where we need some type of protection, whether it's a pressure suit, some type of habitat. So that equals to about almost 220,000 a year. Not too bad, okay, if we get some type of protection. Lower elevations on Mars, it's almost by half. We get only 273 microsieverts per day. What does all that mean? Well, you and I sitting here on Earth, we get about 6,200 a year. As opposed to on Mars, we get about 220,000 a year. Now you're starting to see the levels of radiation and those implications. Recently, Curiosity, who does have a little gamma ray spectrometer on board, they detected a corona mass ejection. And as you can see, on Gale Crater, low elevation, we get about 220 per day. And during a proton event, we get about 600 per day. So how do we detect these from the surface of Mars? We can't. They're unpredictable, right? So we have to figure out a way how to survive on Mars. More importantly, how do we detect these solar proton events so that we can take emergency shelters and protect ourselves. So Evan here, who did some of the math for me, started looking at the implications of what are the radiation hazards on Mars.
So to put it into context, like Antonio was saying, just to break it down, we've been talking about microsieverts and then millisieverts. So the millisievert is basically, it's 1,000 microsieverts, just to ground you all, the 10 to the third. So on planet Earth, in a year, the average human, depending on where they are, if they're closer to the poles, they get more radiation. If they're closer to the equator, they get less. Get between 1 and 6. It's a lot of variation depending where you are on the Earth. 1 and 6 millisieverts per year. All right. So when you're looking at how much radiation a human would absorb over a 3 years on the planet, 6 months there, 6 months back, unless we can get there in 39 days. And I don't know if any of you are familiar with Dr. Chang Diaz's work on the Weissmere. He thinks we can possibly get there in a very short time, which would be really exciting. He's convinced we can. Anyway, currently, given what propulsion systems that we have, we're looking at about a 4-year journey altogether. So you're looking at 4 years, you're looking at about 3,100 millisieverts. this is bad. This is really bad. If we look at the effects on the human body, the first thing that happens, any ionizing radiation, right, actually breaks the base pairs of DNA, actually breaks them apart. The first thing that would happen to you and I is we become sterile, okay? We lose our ability to reproduce. The most vulnerable parts, the smallest parts, when any kind of life reproduces, it starts out simple, becomes more complex, like you and I. As it develops, you're gonna lose reproductive ability. Then you're looking at bone marrow, skin. I mean, you can read it for yourself, and it's cumulative. The effects are cumulative over a lifetime, which is one reason we want to limit things like chest X-rays, full body CTs. You've heard this every day. But what happens eventually? About 500, give or take. Like here, you can see the hourly radiation recorded, Fukushima when that event happened. But in the 3,000 range, you're looking at somewhere between acute radiation sickness, which is going to debilitate a crew. So if we were to do this by the time they got back to Earth, if they got back, right, they're not going to be very happy and they're not going to be very functional. You're also looking at death. About 5,000 millisieverts going to kill about half those exposed. That's if you're exposed immediately. You die off in a month. You're talking about a roughly 4-year mission. You're definitely looking at that loss of human life that goes there. And the people that do come back, they're not going to be particularly happy. So we have to factor this in to any planning, right, that we're going to do regarding getting to Mars, coming back, how we're going to survive there. And this leads us to our next lessons learned. Let's see. Somewhere is this? You got it? Right.
Okay, so what are the lessons learned from the last few slides? The Martian atmosphere is basically almost gone. There's a little bit, right? But it's continuously being stripped away. And the estimates are 100 to 300 million years, it's completely gone. It'll basically become a barren land like the lunar surface. So where don't we want to go? Definitely not the northern latitudes. Too much radiation. The electron volts are too high. Mid-latitude ranges, and we're going to talk about Hellas Planitia is one of the areas that I was researching. Definitely lower elevations. Mars does have a very thin atmosphere, so the lower you are, let's say like in a deep canyon, you get that extra level of atmosphere. It's a little bit more than being on higher elevations. Nevertheless, that still gives you a little more protection from those events. So. And also, when do we want to launch a mission and a return mission? We definitely want to do it when the sun is very active, right? And that's the period where we get a lot of solar proton events. So most missions, if you look on the books, whether it's SpaceX or NASA, it's going to be during the solar minimum. And eventually, we will need some type of solution, right? We can't live in caves the entire time we're on Mars. We're going to need some type of, and there's a lot of solutions on there. We can use water tanks because we're going to need water anyway for radiation shielding, thick aluminum shielding. But now spacecrafts get heavier, they get more expensive, so we need to leverage the resources that are on the surface of Mars. The best case scenario would be living underground, and those would be lava tubes. Lava tubes are important because the research that I'm going to show you now not only protects us from radiation, but it protects us from other nasty stuff. Dust storms, plecorids, the bombardment of meteorites, all this stuff that can potentially destroy your habitat other than radiation, we can be protected underground. Most studies have shown on the lunar surface, Martian surface, we get about 10 to 20 meters of regolith, and that's plenty to protect us from the radiation. So what's a lava tube? Lava tubes are produced by, you guessed it, lava, right? It's mostly by something we call pahoehoe lava. It comes from Hawaii, the term. And what happens is we get nice lava flow. They're happening in Hawaii right now. In fact, somebody was killed the other day. Did you guys read that? Somebody fell into a lava tube and was boiled to death. That's pretty bad. So lava tubes comes to below the surface. And as it dries up, we start to get this nice little shell. And eventually, as the flow stops, we get a really nice lava tube. And some are small, like really tiny, like you can barely crawl through. And then some of them are large, like the ones in Hawaii, New Mexico. This one in particular is in Flagstaff, where this is one of my students. And you can see that they're deep, they're cold, some are very narrow. You can easily fit a habitat in there. You can possibly pressurize whatever holes and gaps we have and use those as a resource. They're found throughout the United States, California, the Four Corner States, Hawaii, mainly where there's ancient volcanoes or active volcanoes. You can find these just about anywhere. So how do we find lava tubes? How do we find lava tubes? This is where my planetary science geophysicist background comes in. How do we find them from orbit, right? What is it we're looking for? Scientists, we got probably some scientists here. We have a very limited budget, limited work week. So we have to concentrate on what are the clues that I need to find lava tubes. The first one is I am looking for skylights or pit craters. And we have to know the difference between a pit crater as well as an impact crater. It's really easy. Pit craters are usually perpetual darkness. They're black. There's something there. That's a hole, possibly something underneath. We can't see much from here until we analyze that actual feature. We can separate that from an impact crater. I get a lot of students telling me, I found one, and then we look a little closer. It's actually impact crater. Most atypical craters do not have any ejecta blanket, do not have any raised rims, definitely no uplifting in the center, and we can actually deduce these and start concentrating on these. What are skylights? They're basically sinkholes. Any Floridians in here besides myself? Yeah, we know what sinkholes are, right? We get very thin and weak light regolith beneath, and whether it's a geological feature, an earthquake or something, the top will collapse, and then we get the skylight entrance. Sometimes the trench will collapse, and we get the Riley entrance as well. From space, we can see these, right? However, not too often, unless you're walking on the surface, can you actually see the entrance from a Riley perspective. So how do we look for these? How do we look for these on Earth or as well as on the planets? We found them on the moon. I think there's some studies now that we've possibly seen these on Europa, and we could talk about that later. So here's a typical NASA high-rise image that I downloaded, really easy. And I like to look for, these are all pit crater chains right here. When there's one pit crater, we call that an atypical pit crater. And where there's a series of them, we call that pit crater chain. Sometimes these pit crater chains, as you can see, this trough, this is what we deduce is a lava tube underneath that just partially collapsed. Okay, regolith gets weak, some geological feature, whether it's an impact next door, an earthquake. We know Mars is now getting Mars quakes, potentially. And then we can highlight those, and we can look for areas where there's no pit crater chain. So in between this pit crater chain, we potentially have a lava tube. In between this pit crater chain, etc., we have this lava tube. Sometimes, if you get enough funding and you can get a tasking, we can task the spacecraft to get a little closer or come at a different time, maybe during sunrise, and now we can actually see a little better. We can see the entrance of a typical pit crater here on the Martian surface, and we get a little closer. That's 150 meters, and we can see there's something in there. How do I know? Well, I can't get to Mars, I can't get to the moon, but now we have something called analog training. Who's heard the term comparative science? Comparative astronomy, comparative planetology. If I do a research on Earth and I come up with some deductive conclusion and I see the same exact feature on Mars or the lunar surface, I can deduce that that geological feature probably is the same on Earth. So one of the analog trainings that we have done recently, and this was a few months ago, is in New Mexico and Arizona. Here in New Mexico, we have a pit crater chain. You can see that the trough collapsed. And then we have the skylight, and then the entrance to the actual lava tube. On Mars, here's my comparative science. We have about the same thing. We have a series of pit crater chains, a nice trough right here, and then the entrance to the skylight. I'm a very outgoing guy. I love to get a little dangerous, and here I am actually scaling inside the lava tube here in New Mexico, and there you can see from inside is the actual skylight. This went in about maybe 800 meters. I have a video of that later. So this goes in about 800 meters, and then I just hit a dead wall right there. So I know that potentially on Mars we could possibly see the same thing if these geological features on Earth are similar. So if we go back to those two slides, where on Mars do I want to actually land my spacecraft with humans and potentially spend the next couple of years there doing research and colonizing? I definitely want to be somewhere in the mid-latitude ranges and possibly in low elevation areas where there's even less radiation. One of the most profound areas is a place called Hellas Planitia. It's a large basin. We think it was formed by an impact crater during the heavy bombardment area a few billion years ago. It's pretty wide, too wide for me, for example. It's 2,000 kilometers long, but it's deep. The basin is deep. Thus, like as I said earlier, we do get almost 7,000 meters of extra atmosphere. Very thin atmosphere, but if I'm over here as opposed to over here, I do have a little more atmosphere that'll protect me from the levels of radiation. And that's a pretty neat place. And if you look at the difference in radiation, you can see that on the higher altitudes, we get about 547 microsieverts. And the lower altitudes, we get about half of that, 250 microsieverts. So now I kind of found my place. Mid-latitudes, very low elevation. Now I'd actually have to find my lava tubes. So where do we find lava tubes? Next to a volcano. There we go. So Mars has lots of volcanoes, but there aren't that many in Hellas Planitia. Hydriscus Mons, however, happens to be in just at the edge of the basin itself. It's nice. There's my my caldera there, Hydriscus Mons, and what you see here is my area of search. All this right here is actual ancient lava flow. I suspect along this lava flow, I'm going to find some potential lava tubes. We can skip that. So how do we look for lava tubes on Mars? There's something called the PSD, Planetary Science Data. A lot of you guys probably have access to this. It's real easy. If you're part of a university or something, you just sign up and you get access to the HiRISE and the CTX data. So HiRISE is a space, so the Mars Reconnaissance Orbiter, which is part of the Mars Science Laboratory, it's a spacecraft currently in orbit, has several cameras on board. The two I'm focused on is the high resolution camera and the context camera. And if you go back to the previous slide, that's my area of focus over here. And I can zoom in, and here, HiRISE gave me about 5,000 images. And that's a lot. I looked at about 1,200. That took me about 6 months. But I was focusing more along the lava flow. So once I find my candidate lava tubes, I can easily upload that to my GIS software. GIS software, you guys are probably familiar with. It can tell me my pixel width, how big of an area I'm looking at. I can zoom in and still continue to keep my high resolution. And I can look at what I believe are my lava tubes. So there's 3 different lava tubes that I particularly was looking at. I did find about 25. However, for a short peer review paper, that's too many. So I like to focus on 3 different ones. The first one is a nice pit crater chain. You can see the pit crater chain in here, just like we see in Arizona. And this is about 1,000 meters across right here. And here's another pit crater chain. And then we have a collapse chain here. So just like we saw in Arizona, I can deduce probably right about here is more than likely, I'm very confident that there is a lava tube in there that we can use for radiation shielding. Here's a nice bowl-shaped pit crater, very difficult to find. Here is my trough, here is my collapsed pit, and in here you can see a potential entrance. You can see the overhang of a possible cave that goes possibly, I don't know, maybe a couple hundred meters, maybe a few miles. But this is definitely what I deduce is a nice pit crater. And then another one of my favorites, because this is kind of a similar one in the Mojave Desert, is just the cavern itself. So here's my trough, my pit crater chain. You can see some collapsed pit craters, very tiny. I can't see much, but if I use Photoshop, I can highlight a little bit and I can see what potentially is an overhang. Perpetual darkness. So if I zoom in really high, I should see pixelation. and that can tell me that's probably just a wall or just bad sunlight, a shadow. But if I zoom in and I get what we call zero pixelation, that tells me it's perpetual darkness, that there's no data. I can deduce that's probably the entrance to a cavern. So I found my hypothesis was, okay, I found my pit craters on Mars. Can I actually use those for radiation shielding? I can't go to Mars or to the moon at this time, so I have to use whatever I can here on Earth. And so my students and I, we went to 3 different states, and we looked at 3 different lava tubes in those 3 different states. There's one, for example, in New Mexico. So from space, there is New Mexico. It's one of my famous, this is called the Ice Cave. It was formed by a lava tube. And you can see a nice trough here. And the pit craters right here, you can see these actually entrances. And this is where the actual lava tubes were, where my students and I went and did our radiation experiments. So what kind of experiments did we do there? We took a Geiger counter, we took a barometric pressure indicator, and we did some experiments. We wanted to know what is the radiation exposure just hanging out here for a couple days. So we took some measurements. We took 20 measurements, each location on the surface, 20 measurements inside each lava tube. We usually do them at solar noon. Solar noon, as you guys know, it's when we get the most proton events in this particular area. And that's when we get the less scattering. And here is, I don't know if we're going to get video. Does this have a speaker?
It's turned off right now.
If we can't do it, I can send you guys the link and you can see this.
Thank you, Elizabeth.
And I can hook up speakers to mine?
Okay, so we are here at the entrance of the Lava River Cave, which is a lava tube, and it's about a mile long. And so we're going to go inside and take about 10 different radiation measurements, as well as barometric pressure, temperature, and things like that. And then we'll turn around and go hit the SP volcano, which is about 45 minutes from here. Okay, so we're entering the lava tube now, and we've got about a mile to go. This was a big one. This one's about just over a mile. It's actually quite precarious here to walk on this lava flow. If you don't have a good footing, you can trip and break an ankle, even worse. Okay, so we're inside the lava tube, and
I don't know why I'm whispering.
Carly and Lawrence are running the experiments. And we're about 400 meters in, and there's our first beep. What's the count?
0.197.
So it's 0.197 microsieverts. What's the temperature in here?
50.7 Fahrenheit.
So it's gone up about 3 degrees, close to 3 degrees. Cool. Radiation has gone down a little bit, about half, and we're just going to wait till the sun is at solar noon to take the reading of the day.
Actually, I think it's gone down more than half. It was 0.21 at the surface, and we've gotten down to 0.05 down here.
Yeah, so they go down more than half, which is consistent with the other 4 lava tubes. It goes down to about 82% difference. Okay, so let's look at the results of those experiments. So here are my 5 lava tubes. As you can see, the average was about 0.458 microsieverts per hour. And inside the lava tubes was about 0.0784 inside the lava tubes. As you can see, that is a big difference. You can take an average equation in there. I'll spare you the pain. It comes about to 82% reduction in the radiation exposure as opposed to the surface. So that's not too bad. Now, if I use deductive reasoning and use the same math, on Mars was about 342 microsieverts. If I deduce the 82%, I am now at 61.64 microsieverts. And Evan can tell you what are the benefits of lava tubes on Mars.
So in a nutshell, we've gone from, if you remember earlier, we were at over 3,000 for roughly a 4-year mission. All right, now you're looking at about 88 for a 4-year mission. So this puts you, much further down in the realm of survivability. You're bordering between tolerable levels and moderate risk. Okay, so the idea that we could use these as sort of ready-made shelters, I think is actually, we've gone a long way towards looking at potential landing sites. Obviously, the lower regions where there's lower relief, like Hellas Planitia, you've got more atmosphere, you've got less radiation, and you can use these as shelters, like Antonio said earlier on, not just for the radiation, but for the dust storms, for micro bombardments. You've got something there. What I think is really interesting, the next phase, and this is, leading into the realm of, what really excites me, the sort of imagination. Many of you have read Robert Zubrin, I'm assuming, and I'm going to intone him a little bit. The farther we go, the farther we will become able to go. But just in terms of pure research potential, you're looking at environments that could show you, will give you information about an earlier time on Mars. What might we find, in these lava tubes, in shelters on Mars? There are some, plans to maybe get some rovers that could go down into them. I hate to see, a multi-million-dollar rover turn upside down while trying to go into a lava tube, but be that as it may, the most exciting thing I ever heard was from a speaker who said that a geologist on Mars could do more in 15 minutes, could learn more about that planet and its history in 15 minutes than all of the probes that we have sent there, from the Mariner program to today. So, is it worth our while to get humans on Mars? I think unquestionably. There are so many reasons why we should do this. Now, what can we find? On Earth, what are we impressed by? We're impressed by life that can exist in harsh environments. I believe you made mention of a talk later this month that your group's going to do. These extremophiles. So we've identified lots of extremophiles here on Earth, ones that can live in extreme alkaline environments. One of the more interesting ones was discovered purely accidentally in a food processing plant about 60 years ago. They used to irradiate cans of food, and then they found this one thing that was resistant to radiation. Deinococcus radiodurans. And this thing can survive, and it can survive. It's actually what they refer to as a poly extremophile, because it's not just radio resistant. It's resistant to drought. It's resistant to pressure, vacuum. The thing's incredible. Now, potentially in years to come, people doing research at the genetic level, we might be able to look at how this bacteria is able to cope with these environments, and look at how we could change our own biology eventually. And this is down the road, but people are doing this right now. This is not science fiction. People are looking at this right now. But I think it's just exciting to think what we might actually find in some of these environments that tell us more about the history, in addition to giving us a place to stay while we're on Mars.
Okay, so to just wrap things up, the lava tube investigation that Evan and I did, as well as my interns and students, took about a year. Most of that was actually downloading and analyzing the data from the NASA PSD depository. A lot of the geology work was done in the 3 states. These are called analog sites, so NASA universities throughout the entire world actually come out here all year long, and they test their space, whatever rovers they want to send, spacesuits, etc. So Moenkopi is a very famous one. NASA actually sends their astronauts out there to test spacesuits and walk around in an environment that looks particularly like Mars or the Moon at night. The Canyonlands as well as the Mojave Desert. Mojave Desert, it's known for the dozens and dozens of lava tubes that are out there, as well as calderas that kind of mimic the impact craters you would find on Mars, as well as the lunar surface. At Death Valley, I am taking my girlfriend in a couple weeks to Death Valley. Death Valley is a highly used analog site, especially for the rover Curiosity. Curiosity actually did some training at Death Valley. And Mapias as well, just out of Albuquerque. There's about, I believe, 17 lava tubes that you guys can actually go out. I put this out here because this is all public national parks and land. You don't need, the only permission you need is if you're going to collect actually rocks, then you have to get a permit. But all these sites are accessible to you guys if you want to go out to these national parks, walk around, take photos, pretend you're on Mars. It's a pretty neat place to go. The only caution is Mapias, during the winter, they will close the lava tubes because it rains and then it freezes out. People slip, they break their legs, and they tend to close these lava tubes during the winter months. So a really neat place for you guys to go out and explore a lot of the public parks that we take for granted. So just to wrap things up, Mars is a really harsh environment, and we're 20 years ago, we're going to go to Mars, whatever, and as soon as we started sending spacecraft out there and Curiosity and all the rovers, we're starting to learn that the environment is actually harsh. Not only from a lack of atmosphere perspective, cold winter months, the time it takes to communicate back home and forth. It's going to be a really, really harsh environment from a physical perspective and also from a psychological perspective going to Mars. One of the interesting things we recently learned was a few years ago when we actually sent Curiosity. The flight to Curiosity had a gamma ray spectrometer, and what we learned that the 6-month trip to Mars, we learned that the radiation was about 7 times higher than we actually factored in during the planning process. So from a human perspective, how do we protect ourselves from that? And as I'm not an engineer, but I know there's engineers out there that are experts in planning these spacecraft missions to protect humans as well, whatever missions we send out there. However, there are some things on the planet that we can use as a benefit, and one of those are the lava tubes, in particular in the Hellas Peninsula. And as you know, when we go out there for one mission, we want to learn more than just about lava tubes. Perhaps inside the lava tubes, we can find, from a astrobiological perspective, can there be something out there? Lower pressures, perhaps maybe there's some indications of water beneath those lava tubes. We don't know. Nevertheless, we do know that the lava tubes can protect us, 82%. And this number could be higher, this could be lower. From what we know about Mars, lava tubes should be bigger and wider. That actually can benefit us. And eventually we want to improve our lava tubes. Perhaps we can actually use some type of habitat inside the lava tube, and then we can build our ways up. Some student asked me the other day online, why can't we just build, use the regolith? There's studies at UCF in Florida to use the actual regolith of Mars to make cement and make buildings. But then, where do we get the water from, right? You can't weld on Mars, right? There's no oxygen. So from that perspective, a lot of the stuff we're going to have to bring to Mars, pre-build, and perhaps put them together like a big jigsaw puzzle. In the meantime, however, just like the early explorers, the Great Migration across the country, we actually had to live off the land, exploit the land, and leverage whatever resources we had initially, and that is where the lava tubes come in. And that's all I have. Thank you very much. And if you have any questions, Dr. Davies can answer all those for you. I'm just kidding. Yes, sir.
Did you do a calculation just what the shielding factor of X amount of rock would be? I'm curious, you did measurements of radiation, but you've also got the natural background of your soil and things like that, which apparently you didn't subtract out.
We did. We wanted to make sure. So we brought in some other instruments to make sure that perhaps there was any copper radiation coming out of those, a lot of those, or lithium, or any type of. So we did check for that initially, and the Geiger counter was showing 0 most of the time. We did magnetics as well, which were negligible. There's nothing coming out of there. And most studies have shown that all you need is about 5 to 10 meters of topsoil to protect from radiation.
Yeah, if you
coated your spaceship with water, wouldn't this give you a lot of protection?
2
from
inches.
radiation?
So most
And then get it from the south pole of the moon, so
Yep.
your gravity is less.
So most studies have shown all you need is 1 inch of aluminum shielding or 2 to 3 inches of water shielding on the moon or on the Mars to protect you from most
Okay.
radiation. So how do we get the water on Mars? That's going to be a challenge, right? It's going to have to be, we're going to have to mine it in there and protect it so it's not lost into the atmosphere or little atmosphere we have. But you're right. Or ice. Ice would be nice. There's even talk about using the carbon dioxide ice as shielding. So that can be used as well.
Yeah, but it seems to me you're saying we would be spending billions just to send somebody to a bunker on Mars.
Sure.
Yeah. So
What's the point? I mean, suppose they want to take an excursion, maybe a few hours, maybe a few days with a rover. Just how much radiation would they get then over the course of a mission?
So right now, if we
In order
would
to do something, you know.
Yeah, if we went to Mars right now and lived in lava tubes, the most that a human in a pressure suit could actually be exposed outwardly on the surface is 3 hours a day, twice a week. That's it. So if as a geologist or as a doctor, if I went to Mars, most studies have shown is that how long can I work on the surface without being protected? It's 3 hours a day, 2 to 3 times a day, a week, and that's it. That's the max.
Now, where is most of the radiation coming from on Mars? Is it from solar or is it cosmic?
It's solar.
So in that case, if you do your work at night,
Yeah, work at night, also during solar minimum. That would be the best time.
okay.
Martian vampires.
If I remember correctly, the atmosphere near Mars has a very large seasonal variation. And did you take that into account in your?
I did not. No, I did not. Mhm. Right there, sir.
Have you looked into the Persian underground canal system?
No, sir, I did not.
It's been several thousand years old, and I've seen them. I've been in them. Some of them underneath the cities are actually dry. We might get something in terms of the engineering from that.
That's a possibility. Mhm. I have not looked into those. I'm sorry, sir.
Back in the pre-Apollo days, there were astronomers who worried about the thermal properties of the lunar surface and got completely wrong conclusions. I remember as a young man working for a man who had been on Apollo planning, and he had very scoffed at theoreticians. He said, they all assured me when I landed on the surface of the moon I was going to sink in dust a mile thick. I'm sure you know what I'm referring to. What precautions are you taking that you haven't made similar errors?
So if I look at the 16, 17 missions that we sent to Mars already, the surface of Mars, it's mostly breccia. It's a very tough material on the surface of Mars, and so the lava tubes as well, I deduce, will be structurally intact. They won't collapse or anything like that. But I've never been to Mars, so I have to use what I have here on Earth, the analog training that we use here, and then we can just deduce, based on that comparative science, that more than likely Mars is probably about the same from a geological perspective.
But the atmospheric pressure is different, or whatever difference that might be.
No, but we sent a lot. We Curiosity rover, tons of spacecraft that we sent. We know what the data is. I know where you're coming to. That all the rovers can tell us one thing, and then when we get there, it's completely different. That's a possibility. You're right, but I think in the last 60 years, our collection of information and our rovers have gotten better than what we did in 1959.
I think what you're saying is you have data from rovers on the site while those.
Exactly. So we have enough data. We have enough spacecraft. I think we have 7 in orbit right now. Where during the lunar missions we had nilch. We had 0.
I was wondering about the flash line base up in Devon Island. Has that been a useful opportunity, or is it volcanic up there, or do they have chances for finding the latitude?
I'm not aware of any lava tubes in that area. Have you looked at it, or?
No,
No.
I'm
Mm-mm. Lava tubes that I've chose came from a budget perspective, so I knew where I can go. There's the laugh, right? How many professors we have here? Okay, you get so amount of money. I couldn't go to Iceland. I couldn't go to Hawaii. I'm bringing 3 students with me, so now I go from Utah. So yeah, it's very limited. The research is very limited in scope, but when I look at the data, I've got 5 separate lava tubes telling me the same exact thing. So that was conclusive enough for me.
You briefly mentioned something about Europa, shielding on Europa. What is?
Say that again?
Europa.
You mentioned something about shielding on Europa.
Yes. So we know the moon Europa. It's a nice moon. Based on tidal friction, we believe that beneath the ice there has to be some type of lava caves. Ice caves like we see in Iceland. They're formed mostly by hydrothermic activity, hot water coming back and forth, and eventually these, I don't know why they call them lava tubes, but they call them lava tubes on Europa. And when you have 30 miles of ice on the surface of Europa, that is enough shielding for radiation on the surface.
Just to add on to what Antonio was saying. So you've got, between the gravity of the sun and Jupiter, you imagine the crust of Europa is doing something like this. So to posit that there may be essentially geothermal activity on the crust is actually quite likely. And when you analyze the ice surface, they're seeing essentially what look like fissures, melt fissures. So they believe that's what they're using to base the theory that there is a liquid ocean underneath that. So in Europa, it's truly the ice, and you've got miles of it. Now, back several years ago, I know Texas A&M University was actually working with NASA to develop a probe that would go into the ice and kind of swim around and see what it could see. And I think that would be fascinating. I think, again, due to budget constraints, that got shelved for a little while at least. But we were actually working on some of the remote rovers on their oceanographic research festival down in Galveston. So stay tuned for that one.
Yeah, I think you said that the lava tubes on Mars are probably bigger than the ones here. Is that because of the smaller gravity and less?
2 reasons. Triscus Mons, for example, or Olympus Mons, larger volcanoes, larger lava flows, and thus we call that dispersion. So the lava flow would be actually wider. So the lava tube underneath it would theoretically should be wider as well.
For terrestrial,
You go.
for terrestrial lava tubes, I recommend the Lava Beds National Monument in Northern California. All of those lava tubes are tourist friendly. You can walk through them. They have steps. Some of them you don't want to down those steps, but there are steps. And there's one cave there, Skull Cave, which is basically huge. I mean, it's bigger than this road, way bigger than this.
There was that. So we did these really early in the morning, and then solar noon, and then late at night. Because in some of these, there was some tourist activity, and we wanted to keep. I know a clean room analogy is wrong, but we didn't want to do experiments with 300 people with their iPhones walking around and doing all that stuff. So we picked these isolated spaces where we know nobody really goes to these, especially during the summer months when it's 120. Yes, sir.
Yeah. Why is it that the radiation on the surface of Mars is much greater than it is at the International Space Station when it's so much further away from the sun and you have a benefit of the atmosphere?
The International Space Station is well within the magnetosphere, so they are being protected by Earth's magnetic field. Once you're outside that magnetic field, so the space station is 150 miles in orbit. That's well within the shielding, so they're protected. On Mars, big different story.
Mars doesn't have a magnetic field, so
No questions anymore? One more, and then I just want to add one thing. Go ahead. Yes, sir. I don't know the answer to that. I do know that when the astronauts did land on the surface, especially during the first missions, they when they came back, and you can read the medical reports, they did complain of some radiation sickness. And one included painful cataracts, nausea, dizziness, all the things that come with acute radiation sickness initially. So you can NASA has really lots of studies on the post medical programs, and they didn't know what they were initially, but then years later we've learned that that was acute radiation sickness from early exposure. So before one last thing, the Mars Insight program, which landed almost a year ago, we're starting to actually rewrite the books on the geology of Mars. We've been now detecting perhaps Mars quakes, right? From it, we thought that Mars was a geologically dead planet. However, we're starting to learn that there are occasional Mars quakes, and that tells us what? Perhaps the core is still geologically slightly active. Quakes only come from two things: activity in the core or tectonic movement, right? We know Mars has zero tectonic movements, but where are these quakes coming from? Perhaps the planet's still slightly geologically active, and that's kind of exciting from a Mars perspective. Okay, thanks for coming, guys. Really exciting news. And I do apologize for the one or two questions I did not have. Email me, and I'll get you the answer. It's that easy. Thank you.